Hello, guys. I hope you all enjoyed this 2022 GATE paper, right? Mechanical was said to be moderate. Not some of the questions were quite easy, some of the questions were quite difficult, but if you take a general perspective, it will be a moderate thing. So in this video, what we are going to see is the questions related to materials manufacturing and industrial engineering in paper 1. So subsequent videos will be there for paper 2 as well. So coming to this part, the materials manufacturing and industrial engineering. So as I told you, some of the questions were quite easy in this thing, but some tricky questions are also there, and also MCQ and MSQ questions were also there in this topic. So let's don't waste our time and go to the questions straight away. Okay, so this question was a MSQ question, multiple selection question, right? From the heat treatment related to surface hardening. So the question is, if which of the following heat treatment or process or is or are used for surface hardening of steels? Okay, so we have learned almost all the techniques which are used for surface hardening. So we know that carbonizing is one of them, carbonitriding is one of them, and cyaniding is one of them. But annealing is not a surface treatment option; it's a heat treatment option. But that's also used for generally for stress relieving, not for hardening. So this question was quite easy. So carbonitriding is you will be carbonizing. You will be using. There are different techniques. Cyaniding also there are different techniques, and carbonitriding is also used for surface hardening. So the question, and the person who has read something about heat treatment or surface treatment would be able to answer this one. But okay, don't worry. Even though you get it wrong, if you miss one of this, still you will not get a negative mark. Okay. So this answer will be A, B, and C. So the answer will be A, B, and C. Those who A, B, or not B, A, B, and D. Okay, B will not be there. So those who write all these three right will get 1 mark. Okay. So that was from the materials parts. And there is another question from the materials. It is from the iron carbon diagram. Okay, so simply we will call it iron carbon diagram. Sometimes there is iron carbon diagram, right? Now it is asking about the eutectoid composition. So the where below this around this 275 degrees Celsius. So the eutectoid reaction is happening at 275. It's an invariant reaction, right? The temperature at which it is happening is 275 degrees Celsius. That we already know. The maximum solubility of carbon in alpha ferrite phase is 0.025, 8% of carbon. A steel sample having no other alloying element except 0.5% 8% of carbon is slowly cooled from 1000 degrees Celsius to room temperature, right? The fraction of eutectoid, pro-eutectoid alpha ferrite is in the above sample of the temperature is. So if I plot only that part, the bottom part of this iron carbon diagram, so this will be suppose this is the ferrite and it is already a small composition is only for alpha ferrite. Suppose this is the eutectoid temperature, this one, or eutectoid point, you can say 725. Now this, what is this corresponds to 0.025. Okay, and we know that there will be one more line which will be coming here. This corresponds to 0.8, right? Where above which will be completely austenite, and below which it will be a combination of our ferrite as well as cementite. Okay, so this will be the typical. So this is 0.8, and we know that what is happening here. This will be 6.67. So which we will call iron carbide, from which the name came, right? So our temperature, our composition is 0.5%. So 5 will be lying between this thing. So suppose if this is 0.5%, which is of our interest, and suppose it was taken in 1000 degree and it is cooled, right? So this is the point of interest. Now, if so, what it is asking is the fraction of pro-eutectoid alpha ferrite when the steel reaches to room temperature. Suppose if this is the room temperature which can be reached, right? What will be the here? What will be the composition when it reaches to this one, right? Now what will happen? So this is completely gamma or austenite, and this will be alpha ferrite. Okay, So why it is not as proeutectoid? So it is happening before before this proeutectic reaction, right? So this is the eutectic point. So proeutectoid proeutectoid alpha ferrite will come here only. So whatever ferrite. So whenever this point reaches this curve, what will happen? Our ferrite will start forming. So till that it will be fully in the gamma state, right? But after that, what will happen? Whenever it touches this point, ferrite will start forming, right? What will be the composition at here? You can use the, so you can plot this thing. Your it's not the composition, fraction. So what if you plot this thing and take the river rule? You can use the lever rule to find the composition at any point, right? So what will happen? It will reach here, this point, just above this one. What will happen? We will have the maximum composition of ferrite, because at that point, what happen is, what we have here is alpha plus gamma, right? Alpha plus gamma will be here, right? So whatever alpha will be formed will be proeutectoid, because this is the eutectoid point, and whatever happens before this one is known as proeutectoid. Okay, so it is asking, if I take any gamma percent here, I will get the total gamma percent, right? But what it is asking, only the proeutectoid gamma. So what will, suppose if I draw what is happening here, suppose if gamma is in the still the solid state, suppose these are the crystals of gamma which is already formed, right? If I come here, what will happen? You will see some of the gamma will convert into so this will be remaining as it is. Okay, so you will see that some of the portions you will see ferrites as well. It will be deposited almost in the towards this one, towards your drain boundary. Now here what will happen is, we will see again it is still solid. Okay, you will see much bigger size of gamma here, and what we will see here is this will remain as it is, and the rest of the gamma will changes to what we know is the alternate lamellae of ferrite and cementite, which we call pearlite. So this is what the rest of the things will tend to pearlite. So the question is, how much is this? Suppose if I mark, if I use another ink to mark our ferrite, suppose this is ferrite, this is the ferrite which is forming. So change in color will identify. So this is ferrite. Whatever is red is ferrite, right? Alpha ferrite. Proeutectic alpha ferrite. This is also in pearlite also you will see ferrite, but that is post, you can say, eutectoid ferrite, right? So the question is how much this is, right? So if I want to know that thing, so I have to take the composition here or the tie line here. Suppose if I make a tie line, and if I want to know what is the composition of alpha, so this is the gamma side, and this is the alpha side. This is alpha, right? This is gamma side, right? If I want to know what is the fraction of alpha which is formed, we can go for the lever rule. So lever rule will tell you what is the fraction of both, right? So suppose if I take the opposite, so in the lever rule, this will be my lever. Okay, so this is the opposite. Suppose if I want to have alpha, I have to take the opposite lever and the total lever length. So divide that thing, you will get the fraction of this. So what will be the opposite arm? So this will be 0.5, you know, and this is 0.8, right? So 0.8 minus 0.5. Fraction of alpha will be equal to, I will say, opposite arm, total arm, which will be equal to 0.8 minus 0.5. But what will be the total arm? Suppose if this is the point, so it will be 0.25. That's already given. So 0.8 minus 0.025. So this is coming to be 0.3 divided by 0. This is 0.775, right? Let me calculate. 0.3 divided by 0.775 will be coming to be 0.87. 387, 0.387. So that is answer, and exactly that answer is given here. The A option will be the right answer. Okay, so this was a simple problem from the using our from the ion carbide diagram. We can use the lever rule to find out the I hope most of you will be able to make this question correct. Okay. So if I are convinced, we can go to the next problem. Yeah, this is from the inventory. Which one of the following is not an form of inventory? Raw materials, CNC milling machines, work in process materials, and finished goods. Okay, so it was quite simple, and everybody knows that what are the things which is happening, what are the things which is considered as inventory. So raw material will be considered as an inventory. Working process materials is a form of working process. We will call it working process inventory, right? Finished goods kept with us is also inventory, because unless and until it is sold, it is still an inventory to us. But the machines that we buy, it's not an inventory. It's our what do you say? It's our capacity, or it's our asset, because that is not taking part of inventory. So the materials that we use and the support systems that we have is not an inventory. This is asset to us. Okay, so this will not come as inventory. So whatever we buy for, which is directly taking part, which is going as a product. Suppose if I buy copper to make copper pipes, so copper is as a raw material is a inventory. When the copper pipe tubes are made in between process, that is an inventory. When it's finished and it's kept with us, that's also an inventory. But not the machines which is used to make the copper machines, copper tube to give that form. Okay, so CNC machine is not the inventory. So this will be our answer. Answer will be this. I think it's a multiple selection question. So only means I don't know whether it's a multiple choice or selection. So please pardon me for that. I only have the questions, but I don't know whether it's a multiple choice or multiple selection. But I am quite sure that this is a multiple selection question, because there are plenty of answers, right? This one, but this, the answer will be B. Okay, so it's not. It's asking which is not the inventory form. Okay, now. Which of the following method can improve the fatigue strength of a circular mild steel shaft? Okay, so this is also a multiple selection question. Okay, so fatigue strength of the mild steel shaft. So in a shaft, you can see that what kind of loading is happening. Shafts are generally used for transmitting power, right? So it will be connected to externally connected to any of the any of the parts, which is rotating parts, right? Two shafts could be connected. It can be shaft to means a power drive. It can also be possible. So there are multiple ways it can be connected to a power transmission system, right? So in that thing, so what could so a cyclic load will be happening in the shaft, right? So there could be fatigue which can be possible. To eliminate the fatigue, we can use many other techniques. So it is asking which is not the technique, or which is the technique, which are the techniques which can improve the fatigue strength. We can always short peening is a technique which is used to improve which can improve fatigue legs, because in short peening what will happen is you have a workpiece and you take balls, so small balls, metallic balls. Okay, you can decide the material based on what kind of strength or what kind of how surface has to be. Suppose sandblasting is also there, but short peening means you use metallic balls and it will be impinged, means it will be asked to in a high velocity, it will be hitting this thing. So what will happen when it hits this thing, the surface of your requirement? So this will create a stress here, right? And whenever the stress is means high, means when this was taken above the your yield stress, so what will happen? A slight deformation will happen. And also because of the hitting of this ball, what can also happen is your temperature is also somewhat higher, right? And this will create what we know is your strain hardening. When the strain hardening happens, only because since it is sitting here only, so only the surface of the balls are very small, so only the surface will get harder. So short peening is a technique used for surface hardening. Okay, so generally your what you say, your gears are used to be toughened or hardened with short peening techniques. Okay, so shaft can also be used. So in that way, what will happen? The stresses it can take in the periphery will be quite high. So the fatigue strength, even though the cyclic loading will happen, your surface will be still hardened, still strong. Okay, so that your fatigue strength, and make sure that only this is done for certain materials, because if it's a brittle in nature, so it can create cracks and it can create you weak. Okay, you have to select your material and you have to select your short peening, means the ball material is also a critical factor, and the diameter of the ball is also a critical factor. Velocity is also a critical factor. Okay, so short peening can also can be used for strengthening and improving fastening strength. Now, relative humidity, of course, we know that this is an MS-tube, right? So one of the material which can be used for which is used for short peening, means which can be performed short peening operation, is MS. Okay, now relative humidity is a factor. Yeah, this can affect. Why? Because MS, if it's exposed to atmosphere or humid atmosphere, what can happen? The reaction will happen, oxidize it very fastly, and the rust will be forming. So that's why many of the places where you use MS seal will be having with a anti-humidity paints or non-moisture absorbing kind of things, right? So, so if we can reduce, or if we can use MS plates or a MS shaft in a non-humid environment, that will be better, right? So that it can reduce the atmospheric, the reaction with atmospheric oxygen, and reduce the contamination, so that it will improve your fatigue life. So this is also one of the things. Enhancing surface finish, yes, this is also a factor. That's why many of the some of the times you will see that it will be very smoothly finished, and sometimes we will apply some to improve the finish. We will apply some other additives, or we can go for a chromium coating. Chromium coating will help you to, so chromium will be inert and it will not react with the thing. That's also one thing, and also it will give you a good surface finish. Okay, surface finish is also a factor which can affect your fatigue strength. If you give much good surface finish, so that your fatigue strength can also be improved, right? But relative increase in relative, so the reducing, see, whenever this conflicting two things are given and it's asking one of the property is true, so we know that if reducing is true, then increasing will be false, right? And if you increase the relative humidity, what will happen? Your material, the open part of your material, will be exposed to atmosphere, and it can make some rust, and your fatigue strength can reduce. So this will be our answer. So this is the wrong statement, and this will be our answer. So sorry, this is not the answer. Actually, this is a multiple selection question. So these things are answer: A, B, C, and A, B, C true, B false. So A, B, C is the answer. So those who write all the three correct will get 1 mark. I think it's a 1 mark question, and rest will not lose any mark. Okay, fine. Let's go to the next. Which of the following additive manufacturing process techniques are used to wire as the feedstock materials? Okay, so when I took the classes, I have already told about this what are materials which can be used for additive manufacturing. Stereolithography will use the liquid resin as the. So this will be liquid resin will be there, and you will be having a laser head or a photo. Means UV can also be used for some cases, right? So whenever your light source, maybe it could be, most probably it will be laser. When your laser source hits this liquid resin, wherever it hits, will be having started this polymeric reaction, and that will become solidified. Rest of the liquid will remain as it is liquid, right? And when we remove all the liquids, what we get is the already solidified object, which is of this resin material, right? So liquid resin is the stereolithographic material. Selective laser sintering will be used as polymeric powders as raw material. So it's a powder-based technology. Here also you will be using a laser head. Wherever the laser points out, it will become the polymeric reaction will start, and this polymeric powders binds together to form a solid object. It will slightly melt, and it will become the cross linking of the polymers will happen between these powder particles, and that's how the the solid material is formed. Rest of things remain as powder itself. So after the completion of the product, we can remove the powders and get the solid form. So that's the thing. Fuse deposition modeling is using your wire. It could be mainly powders, means polymers. So wire will be fed to an extruder. Extruder will heat the workpiece, the wire, and it will melt the wire and will deposit. That's how deposition is happening in the fuse deposition modeling. So wire is used, and that is our answer, right? In direct energy deposition process, you will use high intense radiation, maybe electron beam, or it could be laser as well, but generally used for metal deposition. So high energy radiation will be used for, and you will be using as a filler metal, so filler material, or a powder. It could be a powder, or it could be straight wires. So that will melt and deposit. So it's similar to what you can see in a welding process, but it is very much controlled, and the process parameters are also very different. So wire as a feedstock will be used for fuse deposition models, and this will be the answer. I think most of you would be able to do that. Now we are coming to the problem. I think these are the 2 marks questions. Okay, the first thing is so this is from the orthogonal machining, right? Under the orthogonal cutting condition, turning operation is carried out on the metallic workpiece at a cutting speed is 4 meters per second. So you please see it's 4 meters per second. And orthogonal rake angle is 5 degrees. So our alpha is 5 degrees. Uncut chip thickness, or T, will be equal to 0.2 mm. And width of cut, B, will be equal to 3 mm. I'm using my convention on this thing, right? Okay, suppose if you are comfortable with your convention, you can take this alphabets as your own. And in the operations, the resulting friction angle is 45 degrees, right? Friction angle, beta, 45 degrees, and the strength of your workpiece towards the shear strength of your workpiece is 1000 MPa. Okay, these are the things that we are required to solve these things, and what we are asked to find is the cutting force. Cutting force we have to find out. So cutting force we are represented with FC, right? FC we have to find out. Now from this thing, from your shear strength, you can always find out your shear force. And if the angles are given, then if you when the shear force is here, you can see no forces are there, right? So at least one force is required to form our merchant circles, from which we can find out our FC. So if I make my merchant circle, so let it be, this is my FS, this is my F, oh sorry, excuse me, let me redraw it. So this will be my resultant, and this, if this is alpha, and this is the thing. Okay, and this needs to be joined to this. Sorry, this is, please pardon me, I'm not so good at this one. So this will be my phi, right? This is my beta. So this is a FT, cutting force and thrust force. This is the FS, shear force, and its normal, the N, and this will be your frictional force. It will be, so this will be your 2, right? This angle will be alpha, and this will be frictional force, and it's normal, right? So this is your merchant circle diagram. So we are not interested in these things. We are only interested in FC and FS. So can we find out FS? Of course, we can find out FS. What, using the formula? Your area, what will be AS? Shear area will be equal to what? T into B divided by sine phi, right? So we know all the things. So T is 0.2 into B is 3 divided by sine phi will be equal to 25. So this is coming to be, I think, 0.2 multiplied by 3 divided by sine 25. 1.49 millimeter square, right? Now what about, what will be our FS? FS will be nothing but our towers into AS, right? Your shear strength multiplied by area will give you the shear force, right? So what will be this one? So this will be 1000 multiplied by 1.419419 anything. So this will give you 1419.7 Newton, right? This will be Newton. Now once you get one of these forces and the rest of the angles, you will be able to solve it, right? So what will be our resultant? So you can also write the resultant will be Fs will be equal to R into cos phi plus beta minus alpha, right? That formula, and that will be the same as Fc divided by cos beta minus alpha, right? Or I can write R is equal to Fs divided by cos phi plus beta minus alpha, which will be also will be equal to Fc cutting force. If it is given, it will be cos beta minus alpha. So from this one, we don't have to find out R. We can directly multiply this one, which will be equal to Fc is what we have to find out. So cos beta minus alpha by cos phi plus beta minus alpha multiplied by Fs. You can find it out. So beta is 45, alpha beta is 45, alpha is 5. So that will be cos 5, cos 40 divided by 5 plus beta minus alpha. This is 40 and 25 will be 40 plus 25 will be 65, right? Divided by cos 65. This will be a fraction 1.81 multiplied by this 1419.7 will give you 2573.3. 2573.4 will be the answer, and this will be Newton. What's the Newton itself? Yeah, it will be Newton. So this will be the answer. So those who didn't make any numerical mistakes, or I don't know, I have made a numerical mistake or not, but still, if there is no numerical mistakes, this will be the answer. So 2573.4. Okay, I think most of you who had practiced something about this motion circle could be able to get this course line. Okay, so this was also a very simple question. No trickiness or this thing is there, just some computation is there. Only in the knowledge of motion circle will help you to answer this question, and you will get 2 marks. I think it's only a 1 mark question. Yeah. Another thing is from CNC. CNC work table is driven by a linear. I think there is no question from CAD this time. Okay. Direction by lead screw connected directly to the stepper motor. So it is saying that the lead screw is directly connected to the stepper motor. There is no transmission system or any gear mechanism is there. We don't have to take the gear ratio. That's all. Pitch of the lead screw, or pitch, will be equal to 5 mm. What is pitch? When one revolution happens, how much linear motion is happening? That's known as pitch. The stepper motor completes one full revolution in 600 pulses. 600 pulses. What is one revolution? How much I will move in my revolution? Exactly, I will move this pitch, right? So 5 mm motion will be happening. Suppose if I send one pulse, how much I can move? This 5 mm divided by 600, right? This will be with one pulse. The motion in the linear motion which can happen in one pulse, which will be equal to 5 divided by 600 mm. This is nothing but our basic length unit, isn't it? So in one pulse, how much it is moved? That is the basic length unit, right? So this will be the basic length unit. Okay, let it be so. If the work table speed is, it's a linear speed it's giving. You can also say that it's speed, right? So we generally use the speed. Our feed is 5 meters per minute of feed. Meters per minute. Okay, but you can say this is in hertz, and this is also in mm per pulse, right? So better you do it with millimeters and seconds, right? So this will be how much? 5 meters means 5,000 mm, and 6 per minute will give you division of by 16, right? Per second. So this will be this much millimeter per second will be the feed. Now, how much will be suppose we will assume that this is the maximum feed which is possible. So it is giving you what should be the capability of your this thing. Your pulse generator, how much pulses you have to generate for this, right? So what should be that? Okay, suppose if this is the maximum speed which is possible, so we have to design for that maximum speed, right? So how much it will be that? So I want to generate a speed of this one, and in one revolution or with a one pulse I can move this much, right? Suppose if I want to generate this much of motion, this much of speed, so I have to send the rate of pulse, right? How much I can send in 1 second. So that's actually the being asked, right? So how much it will be? Just it is nothing but your feed divided by your BLU, right? So what will be your pulse feed rate? Also, you can think like this will be in meters per second, millimeters per second, and this will be in millimeters, right? If you can divide this divided by this one, so this will be in per second, that will be exactly what is known as hertz, right? So in the dimensional analysis also you will get the same. So this will be divided by, means it will come here. This will be 5 divided by 600. So 600 will go up and we'll cancel with 60. So it will be 1 and 5 will get cancelled. This will be 10,000. 10,000 pulses we have to feed. That means we have to input to get a motion, a linear speed of 5 meters per minute. So this is actually what it's asked. So this will be per second, which is nothing but hertz. So this will be 10 this kilohertz. Okay. So it's a simple question. You don't have to know any formula for it. By just understanding what it is given, you will be able to answer this thing. Okay. So in one pulse, I can move this much. The feed which I require is this much. And so for getting this feed, how much pulses I have to send? That is very simple. So your feed divided by one pulse motion will give you the number of pulses that you have to send. Okay. And also it is given that there is no missed pulse. Okay. So this is also a pretty straightforward question. I hope you all could be able to answer this. Now, this is from machining, right? Not orthogonal fitting. Anyhow, it is given that's orthogonal turn. Yeah. Yeah. 1 mm thick cylindrical tube. Oh, sorry, it's not cube, it's tube. Of 100 mm diameter is orthogonal turn such that the entire wall thickness of the tube is cut in a single pass. Okay. So from here we know that what will be the diameter, original diameter of DO will be equal to 100 mm. And what is our depth of cut? See, it's only 1 mm thick tube and it's completely cut, right? So our T, or you can see the depth of cut. You can see D. Oh, let it be T, 1 mm, because we have already used D for this one, right? So our depth of cut is 1 mm, which means that how much I am removing. So what will be the diameter based of the formed this thing, which will be the final diameter. Since it is gone, okay, we assume that okay, this is completely gone. There is no diameter remaining, but you can see that if I'm using the tip of the tool, however I am means if it's a complete material is there, my final diameter will be how much? It will be 98 mm. 1 mm from both sides, it will be 98 mm. But since that is not means there is nothing known as 98 because it's a tube and there is no material inside, still you can assume that your final diameter could be, if it was turned in a with a full stop, it will be 98 mm. Okay, fine, let it be. Means I hope you understand. So it's because it's a hollow tube and this is only 1 mm. Okay, it's completely removed, but you can see the inner diameter, what it is for this hollow tube will be 98. That's only you want to know. The inner diameter is 98 mm. Okay, now what is the what is given? The axial feed is 1 mm per minute. 1 mm per minute. And tube specific cutting energy (6 joules per mm cube). You can see now from this thing. So energy is for joules per watt, joules per millimeter cube, joules per volume means energy per volume is given. Okay. So specific energy, so energy per volume, and we can also equate into what? Your power divided by your MRR. So if you are familiar with this kind of equation, so you will know what it is, right? Your material removal rate is there, your power will be, this will be joules per second, it will be mm per second, and finally we have what you will end up will be joules per mm, right? This is also joules per mm. That's what's known as specific cutting energy. To remove the energy required to remove 1 unit of material. Okay. Now it is asking power required to calculate. So now just multiply this. So if I want to get power, your specific cutting energy multiplied with MRR, so it simply can give you power. So specific cutting energy is given. What we want to find out is your MRR. What is MRR? So this much material is being removed at what rate? So you are cutting at a rate of 1 mm per minute. That will be the actual feed. So if this is the thing, so whatever it is there, so this is pointing like so. If this was the hollow pipe, so this was pointing like this. Okay. So this much material is removed. So what is the area of the material removed? It will be pi by 4 d square, cylindrical, right? Minus d square. The outer diameter square minus inner diameter square will give you the area of the this thing, the material removed. So MRR I will write. And in this direction it is giving the feed, and what is how much it is? 1 millimeter per minute, which will be equal to 1000 millimeter per minute. Or if I suppose I want power will be in generally joules per second, so I can convert into second by multiplying this, means dividing this by 60, so that this will be in seconds, so that all the units will be good, so that whatever I get power will be in joules per second, right? So this you have to compute. I will compute what will be this one. Square minus 98 square into 1000 divided by 60 will give you 518. 51861 multiplied by 6 is also there, 6 joules per minute. So you have to multiply with specific cutting energy, right? Multiply with specific cutting energy means 6. It will be equal to 101.76 watts, which will be equal to 31.10.1 will be that. So 31.1 kilowatts. Okay, very simple problem, right? Only you know we have to know what will be the volume rate with which this material removal is happening. Volume rate is nothing but your area which is being removed multiplied by your velocity, the feed velocity. Okay, and of course this you must understand, so that your specific cutting energy is nothing but your power divided by your material removal rate. Okay, hope you all got the answer. Thank you. And I'm not quite sure about whether I have made a numerical mistake kind of thing. I hope it is not. So please pardon me if I have made a numerical mistake, and you are not allowed. Okay. This is a beautiful problem. An assignment problem is see, it's very simple problem, and only thing is you must know about the algorithms and all, right? Johnson's rule, no, Hungarian algorithm we are using to find out the solution of an assignment problem, right? So it is saying that there are 4 machines and 4 jobs. So and different and it's giving that 4 different machines such that each job is processed exactly by one machine, and one process is exactly and each machine processes exactly one job. That's the condition for this assignment problem, or condition that we are using for applying our Hungarian algorithm, right? The minimum total processing time is found to be, suppose if I'm using the algorithm, this is found to be 500 minutes. And due to change in design, the processing time of the job 4 on each machine is increased by 20 minutes. The revised total minimal processing time is the question asked. Suppose if I have jobs, suppose say J1, J2, J3, and J4, and M4 is there. Suppose I will give the processing time A11 for computing that thing, right? A21, A22, A23, A24. A31, A33, A32, A33, A34, A45, and just to demonstrate it, that's all. Now, how will we make our how will we use our Hungarian algorithm? First of all, we will select whatever maximum in the row and deduct it from all the elements from the row, or whatever minimum in the row and deduct it from all the elements in the row. Do it for this one row, this is row, this row. Then you do it the same for the column, so that we want zeros, right? And we will assign the zeros such that there will be minimum number of lines which is possible for stacking it, right? With which we will do the selections. So this is the process that we are following for using the Hungarian algorithm. Now, see, what will be the next one? What will be the change due to design change? The process. Suppose my assignment was this one. Suppose I assign this randomly. Anything could be this. Suppose if I assign this 3, 4th will be this one, right? Okay. Suppose if I have another choice of these three, the fourth will be different. So this is the minimum. So this is like a A12 plus A23 plus A31 plus A45 will give you 500. This is what is given, 500 minutes, right? This is the question. Now, what is the change which is happening? If it is, this is 500 minutes, but due to a design change, our job for on each machine has increased 20 minutes more. So every for job 4, I have to do every time I have to add 20 here, plus 20 here, plus 20 here, plus 20 here. This is the new matrix which we have formed. Now, suppose we are processing doing this Johnson's rule, right? For the first step, what we have to do, and not Johnson's rule. Okay, every time I'm using this wrong, same mistake. Sorry for me. Sorry, pardon me for that. Okay, Hungarian algorithm. Okay, when we use the Hungarian algorithm, first thing what we do, take the minimum out of it and deduct it from all the elements, right? Minimum out of it, deduct it from all the elements. Minimum out of it, deduct it from all the elements. Now, what will happen here? Suppose there was a minimum. Suppose one of these were minimum and we are deducting it and getting a 0, right? Now all the things are added to 20. Now, if I take 20, if I take the minimum was something, and now what will be the minimum? Whatever is the minimum plus 20 is the now new minimum. And if I deduct this new minimum from the all the excess thing, what will happen? Again, I will end up in the same matrix. After the first iteration, whatever I get the same matrix for the solving this problem will be the matrix for the next one, right? So whatever answer I will end up in the first case will be the same answer which will end up in the second case. Suppose if this was the assignment for the first case, and this will be exactly the same the assignment which will be forming after increasing all the elements, all the jobs by 20 minutes. Now, that is one case. Another case could be, why should I write J1 here and M1 here? Why can write J1 M1 here and J1 here? Or why should I apply the row transformation first? Why not the column transformation? Possible. Of course, it is possible. Now, both the things are the same. If I'm interchanging the rows and columns, or I'm doing the row transformation and column transformation, is nothing but the same, right? I can do the column transformation first, then you go for the row transformation. In that case, one will think that, okay, if I change now the minimum in this one, we don't know. Minimum in this one, we don't know. And we will not end up in the same assignment, right? But believe me, still you will have a solution, right? Suppose if the solution was different, still the solution means if the matrix was also different, still your solution will be the same. You can take one example. You can take any of the row, means any of the assignment problems, and see that if you do the row transformation in first and column transformation next, or in the other way, column transformation first, row transformations next, still you will get the same answer. Okay, here also, even though you have some complications here in computation, because now if I take a minimum from this one, it will not remain. So here it was very easy. You will understand that minimum plus 20 will be the minimum out of here, and if I take outside, the things, the digits coming here will be exactly the same as that of the previous one, right? Still you will end up in the same solution. So whatever the solution is, it is need to be for A45, it could be A43 or A44, right? Sorry, A44. Okay, A44 or A43 or A45. So one of these things is going to be in the solution, and solution will exactly remains for 550. The 500 means the assignment remains the same. So the solution will be nothing but an offset of this 500 with 20, which will be nothing but 520. Why this 520? 520 means 20 is 100. So even though now what is happening here, we are assigning 1 or 0 into these things, right? Suppose if I am giving 1 in this place, 1 in this place, and 1 in this place, which means that we have to add all these things to get the total time. If I add these things, so these things remain the same. Only this thing is offsetted by 20, this or increased by 20, means what? Our 500 will also be increased by 520. Only the solution remain the same, but the value will be 20 offset, right? The total value will also be 70 offset, but because all the things in this row is 20 offset, right? So that's how your answer will be pretty simple, is 520. Okay, but if one of these things was changed, then it would have been a different case. Since all has changed, so no problem will be happening for using that Hungarian algorithm. Suppose if we take the row-based transformation to get it zeros over here, and then we will strike off the zeros using the minimum number of lines, and the number of lines if is equal to the number of rows or columns, then that will give you the optimum solution. And that optimum solution will be offsetted by only 20, since we are offsetting all the things in a single row by 20, or you're offsetting the row by 20. Okay, so 520 will be the answer. Those who write 520 will get the answer. It's a simple one, 2 marks. And only thing that you require is what you were doing in the thing. And another thing is there, some of the people think that there is no data is given, right? But there was no requirement of the data. Only this much will be sufficient to solve this problem. Okay, a beautiful one. Now another one from the product mix or product structure. You can also say that it's from the bill of materials, right? Now it is asking in the product structure, for making 1 unit of P, how much unit of these components are required? So P required 2. If I am making 1 unit of P, I directly want 4 units of A and directly want 2 units of B. To make 1 unit of B, it's for 1 unit is given, right? If I want 1 unit of B, I require 1 unit of C and 3 units of B. And if I wanted to make 1 unit of D, I require 2 units of A. So this is the thing. And now it is saying that I have 50 units of component A as an inventory in my hand. Okay. So the question is, the number of additional units of the component A need to produce 10 units of P. So here I have to produce 10 units of P. Suppose if I want to produce 10 units of P, how much units of A will be required? 40 units of A will be directly required, right? How many units of B will be required? This is 2, yeah. So 2 means 20 units of 2 will be required, right? If I want to produce 20 units of 2 B, how much units of D is required? 20 multiplied by 3, right? So for 1 unit I require 3. So for 20 units I require how much? 60. If I want to produce 60 units of D, how much units of A is required? So 1 unit of D requires 2 units of A, means 60 units of D requires 120 units of A. Okay. Now you tell me, now you will understand, for making 10 units of A, how much units of A, 10 units of P, how much units of A is required? From this way, I require 120 units of A, and directly I require 40 units of A. So total requirement of A will be for producing 10 units of P will be equal to 40 from directly, and 1 is from through this means 120 from this chain. So 120. So this will be equal to 160 units. 160 units of A is required, and out of which we have how much? 50 units is there. So how much we have to produce? That is the question. The additional units of A needs to be produced, right? That will be 160. Additional A will be equal to 160 minus 50 will be giving you 110. So 110 unit will be required. Very simple, very simple. Even with the common sense, you can answer this. You don't have to understand about what are the things which is behind this bill of materials and all product structure and all. With a simple understanding of different levels what is happening, you will get this questions right. I will not call it as a industrial engineering problem. I will call it as a you have your analytical problems, right, in the beginning. So this can be termed as one of them. Now, yeah, this is a purely a welding problem, right? 2 mild steel plates, similar thickness, butt joint configuration, right? So it's a butt joint configuration, and we don't know whether the edge preparation is there or not. Those things are not given, and welded with the gas tungsten arc welding using the following parameters. The welding voltage, welding current, welding speed is given. The filler, so it's using a filler material of 3 mm diameter. Okay. So how? Suppose if I'm making a V joint. It's only saying the butt joint, but we are not sure that Y butt joint or a V butt joint or a simply no edge preparation is required. Suppose we will assume that it's a V butt joint. This is the weld plate. The filler wire is fed at a filler wire feed rate is selected such that the final weld bead composition, the final weld bead is composed of 60% of the volume from the filler and 40% of the volume from the parent. So we know that the weldment and the parallel metal will also fuse. Weld wire is reposed, so wire will be there, wire will be fed, and this will be deposited. Okay, and also we know that the parent metal will melt. So out of this, so this is the, if this is the weld zone, suppose if this was the initial thing, so some of the materials from the parent metal also will be diluted and will be coming to the weld zone, and also the filler material will be deposited. So if this is a volume, or this is the, so this total is the volume, out of which 60% of the volume is contributed by your wire deposition, and 40% of the volume is from your melting of the parent metal. Okay, so this is what is given. So 60% is contributed from the wire melting. The heat required to melt the mild steel is, so the heat required is given 10 joules per meter cube. So this is a specific heat, right? Joules per millimeter cube. So required for melting 1 unit of one unit volume of material, that is given as 10 joules. The heat transfer factor, because this is the efficiency, right? Heat transfer efficiency is 0.7 and the melting factor is 0.6. So both the heat transfer efficiency and melting efficiency is given. The feed rate of the wire is asked. So how will be the feed rate of the wire? So this is the thing which is asked. Now, so what will be the input side? Input side is the welding current and welding voltage. Okay, so what will be, so we can get the power, right? And also we have efficiency terms, right? 0.7 and 0.6. So out of which whatever, so what will be the power? VI is nothing but 20 into 150. Okay, but out of this power, some of the losses is happening, right, because of the heat transfer and melting, right? So in that case, what will be the power which will be utilized? The utilized power will be multiplied by this, multiplied by 0.7, multiplied by 0.6. So only this much power will be used for welding, means the material melting, right? This is the power which is there. Okay. Now, if this is the power which is there, okay, total power which is required for welding. This power is used for melting what? Out of the total volume, 60% is volume is contributed by the filler material feed. Okay, and also you know that heat transfer rate. Oh no, your specific welding energy, right? Specific welding energy is also known to you. Now you can simply write. Let me write it down. That means I will remember these things. Okay, I will write it on the next page. Okay, so I will write what will be the available power. 20 was the voltage and 150 was the current, and 0.7 was the heat transfer efficiency, and 0.6 was the melting efficiency. What it will be? 0.7 into 0.6 into 150 into 20 will give you, oh sorry, 0.7 into 0.6 into 150 into 20, 1260. And what will be the units? Joules per second, right? What will be the heat input per volume? That is what is given as your here, right? Heat input per volume. Will be nothing but your power divided by your MRR, or no, sorry, material deposition rate. You can see that it will be material deposition rate. I will write. Okay, so power is means if I analyze that, this thing will be joules per second, and material deposition rate will be millimeter cube per second. Will cancel this second out, and you will get the your heat input per volume in joules per millimeter cube, right? But this is given. This is given as 10 joules per mm cube, right? So power we know, we know what we want to know is the material deposition rate. So you must understand how much, or you can say, don't think like material deposition, the weld forming rate. So the volume of the weld which is formed per time, how much volume will be volume, or you can say the volume flow rate. Whatever way you want to express it, you can express like that. Okay. So the volume flow rate I will write volume flow rate or material deposition rate or weld forming rate, whatever way you want to write. So this will be equal to, this is the suppose I will take, let it be q dot I will write. So what will be our q dot? Q dot will be our power divided by or that heat input per volume. It will be equal to 1260 divided by 10 will be equal to 126. What will be the unit? mm cube. This was how much? Joules per second. And this will be joules per millimeter cube. So millimeter cube will come here and second will come here. This will be mm per second. 126 mm³ per second. This is what we get. Now, if I told you, so whatever rate in which this weldment is forming, okay, will be equal to whatever will be the deposition, right? Whatever will the wire will be melting and deposited over here, and that's how the weld is forming. But only out of the complete weldment which is formed, only 60% is contributed from the wire deposition. The 40% is by the melting of this one. So that is what is given from here. The 60% is from the wire deposition. Okay. So out of this one, 60% is deposited by wire, right? So 0.6 into this one, Q star, will be equal to what? That will be the volume melted by the wire melting rate. So what will be the wire melting rate? So we know that welding speed is there, right? Okay, welding speed is there, so that we have to multiply it with this thing. So area into welding speed, or you can directly get that feed rate, right? Fine. Will be equal to what? Your area of the welding wire, 5/4 into 3 square multiplied by how much? Feed rate. What is this unit? This will be millimeter square. What will be the feed unit? It will be millimeter per second. So that what you get will be in millimeter square, means millimeter cube per minute, per millimeter cube per minute. So here the same it is there, right? So these are equal. The 60% of the weldment is formed by the deposition of the wire, means that whatever we have find out the deposition rate multiplied by 0.6 will give you this one, your wire melting rate. You can say that feed rate multiplied by your means your area. So if I want to calculate the feed rate, directly we will get it from here. Or what you can find it, this is nothing but your material deposition rate will be nothing but area into velocity. Okay, because the velocity is given. Now only I've seen that velocity is given, you can find out the area, and again you will end up in the same formula. But it will be easy from here, right? This will be equal to 0.6 into 126 into 4 divided by 5 into 3 square. How much it will be? 4 into 126 into 0.6 divided by divided by 9. Did I do a mistake? 0.6. 6 into 126 into 4 divided by 5 divided by 9. 10.69 millimeter per second. Okay, so this will be the answer, 10.69 millimeters per second. Check the dimensions is right, or I think it's a yeah, I made a mistake, right? Your power, no, power divided by heat input. It will be joules per second, joules per second. Now this will be in velocity will be. Did we use the velocity? No, nowhere we use the velocity. I think it's right. Okay, so this will be the answer, 10.69. Suppose, pardon me if I have made any numerical mistake. Okay. Now, this one. Activities A to K required for completing a project. The time estimates and the immediate predecessors of those activities are given in the table. If the project is to be completed at the minimum possible time, the latest finishing time for the activity G is dash hours. So it is asking nothing just to solve this problem. Only thing is, if you have the, I will not say expertise, if you have some knowledge about your how to construct them, how to construct this one, which one, how to construct your network diagram will help you to answer this question. Only thing is to just do the network diagram and find out the critical path. Oh no, latest finishing time, right? So let's start with the first node. So A does not have any predecessor, B does not have any predecessor, and C does not have any predecessor. So that it can start from first node. This will be my A, this will be my B, and this will be my C. So A is 2, B is 3, and C is 2, right? What about B, E, and F are starting from B, and D is from A, and D and E are merging, right? So D and E are merging. D is from A. So D for E 5, and D and E and merging to form H. Okay, and HIJ and are merging. And what about C? G is forming from C, so G can form from C, no problem. And J is from G. This is G 3, and from F, I is formed. F is how much? 4. I, J, and H is missing. So H is from here, I is from here, and this thing is from here to merge to form what? K. So this is K with 3. This is F, E, A, B, C, E, H. H is from D and D, right? H is how much? 10. This is J, I is how much? 8. And J is 8, I is 5. I is 5, J is 8. So this is our network. So we can number it with Fulkerson's numbering: 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 nodes are there, right? Now we can start the forward passing, right? What will be the forward passing? So for this node, this will be 0. For this node, 2, 0 plus 2, 0 plus 3, 3, 0 plus 4, 2, it will be 2. Now 2 plus 4 is there, that is 6. 3 plus 5 is there, that will be 8. So 2 possibilities are there. Which will we take? We will take the maximum. In the forward passing, we will take the maximum. And what about this one? 3 plus 4, it will be 7. And 2 plus 3, it will be 5. 8 plus 10, 7 plus, what is this? Is 5, right? So 12. and 8 plus 13, so maximum is 18. So 18 we will take, 8 plus 10, 18 plus 3, it will be 21. Now we will do the backward passing. I will use this one. In the backward passing, we will start with 21. 21 minus 3, 18. Okay, 18 minus 8, it will be. We have to find out the latest finishing time for G. So we will only do this one, or we can complete the thing and see. 18 minus 8 will be 10. 18 minus 5 will be 13. 18 minus 10 will be 8. Okay. So 8 minus 3 or 8. Yeah, 8 minus 3 or 7 minus 4. 8 minus 5, it will be 3. Or 7 minus 4 will be again 3. So 3 will be here. This will be 10 minus 3. 10 minus 3 will be 7. 3 minus 3 will be 7. So this is the complete list. So it is asking for only G. For G, what will be the latest finishing time? Latest finishing time. So for G node, so if I plot only G, so G is from 4 to 7. This is 2, this is 7, and this is 10. This is 13. No, this is 5. Sorry, 13 is 5. This is 5. Now this is the earliest start, it is finished, latest start, latest finish. Now you know what is the latest finishing time. So latest finishing time is nothing but which is given here. That will be 10. Okay. 10 minus duration was 3, right? Yes. Okay. So we will get what is the answer. So it's a multiple choice question. So the answer is 10. 10 will be the latest finishing time. So just solving means constructing the network and having an idea of the earliest starting and latest finishing times from the network. If you can able to compute, you will get the answer. And it is very simple question. No twist or anything like that. Just construct network and do the forward passing and backward passing. That's all. Okay. Before go forward. Oh, yes. This is another tricky question. Not tricky question. So whoever knows about the shadow pricing will be able to answer this question. Suppose if I have 3 variables or 3 resources are there, right? X1, X2, X3 are the resources. X1, X2, X3 are the resources. So yeah. So there will be limitation for this one, right? No. So I'm sorry. X1, X2, X3 will be the this thing, right? Suppose we have 3 resources, okay, and we have so we have only 2 variables. Suppose it's a product mix problem. So we have only 2 variables. Suppose product 1 is there, product 2 is there. So X1 product is there, X2 product is there. But for making that product, we are requiring 3 resources. Okay. Suppose if I am making cake, okay. So I require sugar, I require this thing, flour, and also let it be butter. Okay, sugar, flour, and butter. 3 resources we require, right? Suppose I'm making two type varieties of cake, and which will be having different profits, right? That's how we just a simple example of the formulation of a linear programming problem, right? Suppose if I do the primal analysis, how it will be? Some A1 X1. The X1 unit of A will be means 1 cake will be produced, and X2 units of 2 cake will be produced, right? X2 will be, this is the maximization function. Maximization of this one will be my this thing. So, and there will be 3 equations, right? Suppose if I use, suppose B1 X1 plus B2 X2 less than or equal to something, some C1, B3 X1 plus B4 X2 less than or equal to something C2, and B5 X1 plus B6 X2 less than or equal to something C3. So this will be the common way of doing it. Now, what we will do if I want to make it inequality to equal signs, if it's a maximization problem, we will do nothing but we will add a slack variable, right, to make it equal, right? So this will be plus S1 plus S2 plus S3. This will be equal. It will become equal, right? So this is how we formulate the problem, and we will add these things in the in our maximization function to get it equal to 0, and then we will proceed with the simplex table like that. Now, what will be my solution? Solution will be one value of X1. X1 will be there, X2 will be there. Now S1 will be there, S2 will be there, S3 will be there, right? Now we have three equations. We are quite sure that how many means what will be our solution. So if I make a simplex table, how many table this will be there? So three equations means in our basic variable function there will be one equation will be there, two equations will be there, three equations. So three rows will be there, right? And if in the end what will happen, we will get some values of x1, x2. Suppose if it is x1, x2, x3, x1, x2, and s1, s2, s3. Okay. Suppose if these two are coming in, or this thing means what? See, there are three basic variables will be there. Okay. Suppose these two variables are coming in our solution. Okay. But we are quite sure that one of these variables will be coming in our solution, right? X1, x2 will be positive, means it will be positive, but one of this will be coming as basic variables here. Okay, so this will be x1, let it be x2, and let it be s3. S3 will come here. That is inevitable, right? Sometimes it is not, only when a small chances are there that this will also become 0, but no, generally it will come. Now take the case of dual. What will be the dual variable? Dual will be a minimization function of y1 and y2. Okay, so I will say z1 y1 plus z2 y2. Okay, so let it be z3 plus z3 y3. Why? There are three equations. So if I take the transpose of this matrix and get the y1, y2, and y3, right? So that there will be, if there are three slack variables, there will be three what? Basic variables, not basic variables, three variables will be there in the objective function of my dual, right? So the number of dual variables will be divided by the number of equations. And if I solve this dual, what will be the basic variables? Suppose y1 and y2 will be there. So only two equations will be there, right? And one of these things will be not there, right? There is only two equations. Suppose if I write it in this one, in this way, what will be this one? Suppose I'll say w1 y1 plus w2 y2 plus w3 y3 will be less than or equal to a1, and w4 y4 plus w5 y5 plus w6 y6 will be less than or equal to a2. So there will be two equations, three unknowns. Of course, there will be in the basic variable, it will coming, one of them will be missing, and that was also obvious. And there will be two surplus variables will be u1 and u2. Let it be u1 and u2. So the total variables will be y1, y2, y3, u1, u2. Okay. So there is the chance that y1 and y2 will be there in y1 or y2, or one of them will be missing, right? That will be 0, and that will be 0. Which one will be 0? I'm quite sure that y3 will be 0, and that's why I'm writing y1 and y2 will be there, because our s3 is coming in this solution. If s3 is coming in the solution, your y3 will be equal to 0. See, your s1 and s2 are zeros. That's why means y1 and y2 is coming in the solution. It does not, if it is 0, this will come in the solution. In the other way also, u1 and u2 is equal to 0. That's why your BB column x1 and x2 is coming as the basic variables. So that's how means I'm not going to the complete details. It will take a lot of time, but this is the general perception or the, and why it is not a shadow price. Shadow price is nothing but, suppose if I increase some values of y1 in our objective function, we will see that the profit will be increased by that much amount, or it will have a proportion. So whatever value y1 will, so our profit will be increased by that much proportion. Okay. So if I'm going to buy that resource, so these are resource values, right? So this will be the, actually y1 and y2 is a y1, y2, y3 are prices. Okay. Suppose if I'm going to buy that particular resource, let's say C3, how much I can pay in the market so that I will still at a profit, or there is no loss for me. So that will be detected by how much I can pay in the market will be equal to y3. So in this case, if for C3 it will be Y3, the value of Y3, C2 it will be Y2, and C1 it will be 1. That's why it is known as the shadow price. Suppose shadow price is actually we are not paying anything, so it's actually a concept only, which means that suppose the question is, if one of the resources is not fully utilized, in this case your C3 is not fully utilized. That's why S3 is coming in this thing. So what will be the corresponding shadow price? Shadow price is nothing but the value of your Y3. What will be that Y3? Y3 will always be 0. Okay. So a person who has a good knowledge about this economic interpretation of your duality, then only you will be able to answer that. But this was a 2 marks question, and it is a multiple choice question, and it was a simple question. The answer was 0. So if a surplus variable, or if a slack variable is coming in your solution, which means that one of the resources is not fully utilized, which means that corresponding shadow price will be 0. Why shadow price can be 0? You can say that it's a price, right? It's 0. Means that you have it already in the surplus. You don't have to buy it from the outside. That's the interpretation. That is economic value that you have to find out. Means you have to understand, not find out. You have to understand. Okay. I hope this is not. I'm sure that this is not clear. It will not be clear in one go. But those I have taken the classes. Means for those students, it will be clear by now. Okay. Shadow price means 0 means a resource will be surplus, or a resource surplus means a shadow price will be 0. Okay. Now this is also a tricky question. People will tend to answer it in a very fast. If it's by mistake, if you didn't see this one, you will end up in but still you will end up in the beauty is still you will end up in the same answer. Okay. So we have a basic line of 25. Okay. Now it's saying that the shaft is, this is the diameter of the shaft. So if I make it in the tolerance diagram, I can find out that this is the shaft. Okay. So 25 is the basic size, and this side it will be minus 0.10, and this will be this plus 0. I don't have to write one minus or plus. It is understood 0.010010. For shaft it is okay. What about hole? Hole, the basic size is given us 25. So that where it will come? So this will become here. So this is the basic size. So it is 25.015 above this one, right? And how much I can go below? 0.15, right? So where we will end up, this is 0.50, so we will end up exactly here, right? And how much towards the top? It will also be 0.05. So this will be my hole. So this will be 25.00, and this will be 25 point how much? 30, or we can say plus 30, 0.030 here. Now this we know. With this thing we will understand what kind of it is there, right? So it is if it was limit to this one to this side, it will be a clearance. This is whole dimension, right? Clearance is there, and sometimes it is in clearance, sometimes it is interference, which means that it's a transition bit. Right? With this figure, you will understand that this is a transition bit. So if the hole size is this much, if your shaft size is coming like this, or coming like this, still it's a transition bit. If there is a marginal difference between this one and this one, only it will change this thing. You know, marginal difference means if it is a clearance bit, this will be this one, and this will be interference. Always interference and always clearance. But since sometimes interference and sometimes clearance means it's a transition bit. Okay. Suppose if you have missed these things and again you try to do these things, how will happen? This will be like this will be what you get if this is the line. Okay, so this will be what you get. Still you will see that it's a transition. Okay, I hope all of you will get this. This is the only trick, only somewhat complicated thing, but those who prepared well could definitely get this answer right, because this was nothing. So how many questions are remaining? Oh, this is the last question, I think. Sorry. Sorry guys, a slight problem was there. So this will be the this is a question which came from rolling operation. So you have a tool roll mill. Okay, your thickness is given. So the thickness of the rolling, your T will be 4 mm. Width of the roll mill will be equal to 100 mm. Diameter of the roll is 200 each, or radius. No, roll diameter is roll diameter. D will be equal to 200 mm. Right. So that your radius will be equal to 100 mm. Fine. The workpiece is lubricated with mineral oil, which is coefficient of friction mu equal to 0.1 mm, 0.1. Your flow stress is given as an equation, and you can see that the sigma equal to 207 plus 414 epsilon, where epsilon is the true strain. Okay, assuming the rolling to be in a plane strain deformation process, and the roll separation force of F for the maximum permissible draft thickness reduction in kilonewton is given, asked, right? But you have also given the equation for that roll separation force. F will be equal to 1.15 sigma bar 1 plus mu L divided by 2 H bar into WL. Okay, where sigma is the average flow stress, and L is the roll workpiece contact length, and H bar is the average thickness of the sheet. Okay, now see, this is sigma. What kind of sigma is there? It's the flow stress, sigma F, you can right? So this is the average flow stress. Okay. Now, only catchy thing is, when will this happen? Let me think. So when will it happen? Suppose if you see the stress strain curve, your stress is actually this line. Suppose if this is the strain and this is stress. So what this means, this is the equation of this flow stress. Oh, sorry, the equation of the flow stress is following a linear fashion. That's why I write it a linear thing. So with the strain, it is not an it is not like a our flow stress curve was there, right? KT it's not a power law of strain hardening. It is not obeying. So it's like a linear strain hardening, right? So this will be, so in this way, if I write, so the slope will be there and the intercept will be there. So what will be the intercept? If I want to calculate from this one, this is the flow equation 207 sigma equal to 207 plus 414E. So if you practice that engineering services questions, so one of the questions were like this. Okay, right. So in this way, so it's a linear relationship. What will be the y-intercept when sigma equal to epsilon equal to 0? What will happen? It will be 207. That's what we'll get here, 207, and this will be like this. So what will be the maximum sigma which is happening? Maximum flow stress. So if we can average sigma will be what? Sigma max plus sigma min divided by 2. Sigma min we know. Now we have calculated what will be the maximum. It will be the corresponding to the maximum strain which is happening, right? So this, if this is max, Emax, then this will be the sigma max. This will be the sigma max. So what? How we will get the Emax? Question is given. The maximum. It is also asking for the maximum permissible thickness. So maximum thickness reduction. Maximum permissible thickness reduction. How will compute the maximum thickness reduction? So that will be the strain at which the maximum reduction will be happening, right? So we have a limiting condition for the draft, maximum draft or maximum thickness reduction. That will be what? Your draft or Dmax will be equal to mu into R, mu square R, right? How much it will be? Mu square means 0.1 square, R means 100, right? 0.1 square into 100 means how much? 1 mm is the maximum reduction which is possible. So now it is 4 mm. So it has to be, it can only be converted to 1 mm in a single rolling operation because of the limitation of the coefficient of friction and the diameter. Okay, so here roll radius is 200, means roll diameter is 200, and so that our roll radius will be 100. 1 mm is the maximum draft. So what will be the strain corresponding to 1 mm draft, right? So your T naught T final will be equal to 3 mm. You can compute the strain will be ln 4 by 3. How much? 0.287. This is a strain means how I can compute strain, because we assume that in the width direction it will not be changing. The width will remains the same. So whatever the area reduction will be happening because of the change in your thickness only. Okay, so that or you can say that 4 minus 1 plus 1 by 3. Still you will end up in the same answer. So what will be the ln 1 by 3? Into it, right? So this is the strain. So what will be the sigma max multiplied by point? This is a true strain, right? 2787 will be how much? Point this one multiplied by 414 equals this one plus how much? 207. It will be 326. 326.1. 326.1 is the maximum, and 207 is the minimum. And what will be the average? So this will be sigma bar will be equal to 326.1 plus 207 divided by 2 plus 207 divided by 2 will be equal to 330. Oh, I made a mistake. 226.55 MPa. So from here we understand that this one. Now it is very simple. Only thing is we know the flow stress. We know the flow stress. This is known. We know mu. We know L, and we know H bar. H bar is how much? H bar is the. It is saying that the average thickness. Average thickness is how much? H bar will be equal to T original plus T final divided by 2. Well, 4 plus 3 divided by 2. 7 by 2 will be equal to 3.5. So 3.5 H bar. So just put that in the equation. F will be equal to 1.15. 1.15 times sigma bar 226.55 multiplied by 1 plus mu by L. Mu is 0.1. L is contact length we have not calculated, right? Contact length is how much? Root of R. RD. Dmax. You can say root of 100 into Dmax is how much? 1, right? So root of 100 will be 10. 10 will be this thing, right? Mu is 0.1. L is 10 divided by what is the formula? L divided by 2H. H is how much? 3.5 into W into L. What was the formula? 2H. Okay, 2 multiplied by H is 3.5 into W is how much? Width is given us 100, right? 100 into this corresponds to a stress, and you might have already seen similar equations like sigma bar will be equal to 2 by 3 sigma F into 1 plus mu L divided by 4 Tm. Kind of empirical relations was there. So it was just a modification of this thing. So for some other material, they have find out some other constants for this. That's all. And multiplied with your WL. If this is also known as the pressure, right? Rolling pressure. Okay. And multiplied with your width and your length of contact will give you the rolling force. So how much it will be? 0.1 into 10 divided by 2 divided by 3.5. It's 1.41. So plus 1 will give you 1.4. 1.14 multiplied by 1.15 multiplied by 2 26. It's 226 only. Let me calculate. 207 plus 326 0.1 divided by equal to divided by 2. 266 actually. So I made a mistake. 266.55. Okay, 0.1 multiplied by 10 divided by 2 divided by 3.5 will be this box. 0.14 plus 1 will be there. 1 plus is the answer. So this multiplied with 1.15 multiplied by 266.55 multiplied by 1000 will give you the answer. This will be 350. 3 Newton. It is asked in kilonewtons, right? The question was to give the answer in kilonewton, 0.3 kilonewton. If you want to display accuracy, exactly this will be. So that ends all the problems which is there. So I hope you could able to get at least most of it. 80% will be very simple. Only a slight understanding will be there. Only for this problem, you have to understand how to estimate the flow stress using the curve equation. Suppose you might, if K epsilon by 10, such a formula could also be there. K epsilon by 10 divided by n. So it can be in different form. It can be fitted to a curve, or it can be fitted to a straight line. Average flow stress. For average flow stress, you can have this graph to find out what will be the average flow stress. Okay, or you can use that integral formula. Integral formula means sigma bar, integral 0 to epsilon, sigma into epsilon, sigma into d epsilon. That means this will be. If I integrate this formula, still you will end up in the same answer. Since it's a straight line only, I use the average like this, the average flow stress like this. Otherwise, you can use the integral formula. Okay. And also, this is this was very easy problem, and this was a trick. Means a very conceptual problem, and a person with a good concept about the primal and dual will be able to simply answer this one. This one was nothing to find out the latest finishing time, just to construct the network and do the forward and backward passing. This problem will be slightly difficult because there are too many data and find out the thing. And also you have to see that this will be how much means I don't know whether I have made a numerical mistake. Otherwise it would be fine. The concept is the same, so you can work it out and see exactly what is the things, or did I miss any also. And very simple, another simple, this is also a conceptual question, but if you know the basics of the Hungarian algorithm, you will be able to find out. This is very simple, straightforward question from machining, some CNC, from orthogonal, from additive manufacturing, your short pinning means surface hardening, your CNC means inventory, iron carbon diagram, also from the surface hardening or this hardening kind of thing. So all the things seems to be fine. I hope you all enjoyed the paper and write your correct answers, and hope you all will get a good score in Gate. Okay, so I will commit with the next session, what will be the paper 2 analysis on the same topics, materials manufacturing and industrial engineering. Okay, guys. So if you could able to perform, I congratulate all those who perform really well, and no problem for those who didn't perform, still have opportunities. A good score will be means I'm not quite sure about what will be a good score in means what will be a good rank this time, because from production part it was quite easy. If you take the analysis of the last 10 years, this will be one of the easiest paper if you take this as the topic, materials manufacturing and industrial engineering. But I will not say this is very simple paper, but very conceptual, and it is a good paper. I appreciate the people who said this paper, because they didn't want to trouble the people, but they want to test what is the depth of knowledge that they have, exactly what it is that is meant for this kind of exams, right? So okay, guys, enjoy. Thank you.